Okay, and welcome back to video 3. In video 3 we are going to learn about finding the rotational inertia of objects by integration. And we're going to focus on the case of a uniform rod. Got some really special graphics here. Alright, if you remember, when we talked about a point mass, we said that the rotational inertia of a point mass is equal to mr squared. So, in general, if you want to find the rotational inertia of any object, you have to do an integral, and the integral is going to involve those same two quantities, except you're going to take the integral of r squared dm. And if you recall, this is very similar as an integral. It's very similar to the integral for the center of mass. Now, don't confuse it with the center of mass integral, but in fact it's very similar in a lot of ways. So we are going to be applying this integral to cases of very high symmetry, such as rods and cylinders and spheres. And in general, the integrals are useful for cases of high symmetry. And you would like to take those special cases and, if you can, use them to represent other objects that might be a little more realistic in shape. So let's take a look at the uniform rod. Okay. The picture up at the top shows a rod of length L, mass M, and it has a uniform density. What we're going to do is we're going to come up with, we would like to derive an expression for the rotational inertia of this rod about an axis that is perpendicular to the length of the rod. And so the axis is shown in the picture. And we want to have the freedom to place the axis wherever we would like along the length of that rod. So if you remember the tables that we saw before, the axis of rotation was through the center of the rod and it was through the end of the rod. Those were two special cases. What we're going to do now is come up with an expression for the axis placed anywhere along the length of the rod. And so we're going to have to integrate to do that. So we're going to start off with our definition of rotational inertia as an integral. And instead of r squared dm, we're going to write it as x squared dm, because we're integrating along the x-axis. And the next thing we're going to do is we're going to play the trick that we played before. What we would like to do is replace the dm in the integral with dx, because it's very easy to integrate over dx when you're talking about the geometry of an object. So what we'll do is we will recognize that the total mass of the rod divided by its total length is kind of like a density. And if the rod is truly uniform, then that density should hold down to infinitesimally small pieces of the rod. In other words, total mass over total length should be equal to dm dx, or the density at any particular point. Then what you do is you rearrange the differentials to solve for dm. So dm is equal to m over L times dx. And that's going to be what gets substituted back into the original expression. So let's see what that looks like. Here we have the formula for the rotational inertia. I have substituted for dm the substitution that we just made just above. And I've also indicated the endpoints of integration. And let's just say a couple things about that. If you look at the picture up at the top, you can see that the axis is going to be placed some distance away from the left end of the rod. And we'll call that distance h. Okay? So when you're integrating here, you have to go backwards by a distance of negative h. That's going to be the lower endpoint of integration. For the upper endpoint of integration, you have to go to a position L minus h. And that's why it goes over here. So effectively, you're integrating from a negative position to a positive position over a total length L. Okay. Next step is going to be to factor out the constant terms. M over L come out of the integral. And we're left with the integral of x squared dx, which is a pretty easy one to integrate. Okay, so we're going to move up here. And of course, the integral of x squared is equal to x cubed. There's a factor of 1/3 that comes out in front. And the endpoints are still written down. Okay, so now we've evaluated the integral. We need to evaluate our endpoints. And so when you do that, you basically substitute in L minus h, you cube it, and you subtract negative h cubed. And let's see what that gives us. Ooh, that's going to give us a fairly messy polynomial, which still needs a little bit more simplifying. Okay, so we've taken care of one of the quadratic terms, but we still have to multiply out the L minus h. And we end up getting something like this. Kind of tedious, but it's pretty easy algebra. And that reduces to the final answer that's in the box here. So when you combine all the like terms, you get an expression for the inertia, which is given in the box. It has mass in it, and it also has length squareds in it. So it has an L squared here, it has an L times h, which is like a length squared, and it has an h squared. So dimensionally, our answer is actually consistent with rotational inertia. We have mass times length squared. Now, in terms of the actual details, L, remember, is fixed. It's the given length of the rod. And we can't do much about that, we're just given that. H is the point that we can decide on. We can choose where we place H. Okay, so I'm going to go back up just for a second to our picture. And you can see that H is the thing that we control. And for example, if you were to make H equal to 0, that would put the axis of rotation right on the end of the rod. If you were to make H equal to L over 2, that would put the axis of rotation directly in the center of the rod. So let's take a look at what happens if we pick those values for H. If you were to substitute H is equal to 0 into the formula that's in the box, you can show pretty easily, and you should probably do this on your own, that what you're going to get is 1/3 ml squared. That's exactly what we saw in table 9.2, and it gives you the rotational inertia of the rod when it's rotated about its end. If you wanted to make H equal to L over 2, that means putting the axis of rotation in the center of the rod, you get the familiar result of 1/12 ml squared. So what we've just done is come up with a very general formula for the rotational inertia of the rod, and we've shown that it actually works out for the two cases that are the fairly common cases that we saw back in the table. And so this is the type of approach that you take when you integrate to solve for the rotational inertia of an object.